Today we will look at the normal distribution function in more detail. The learning objectives for this session are to discuss the normal probability distribution for continuous random variables, the context in which it is useful and its important characteristics. We will also use the normal distribution table to calculate population proportions and perform the transformation of any normally distributed random variable to the standard normal distribution. We will also understand the effect of centering a process and of reducing the variability of a process. In the last session, we described the binomial and the Poisson distributions, both of which are for discrete random variables. We also introduced continuous distributions, such as the uniform and the exponential distribution. And in this section, we'll look further at the very useful normal distribution. So as we presented last time, a random variable x is said to have a normal distribution if its probability distribution function follows this function, where the two parameters mu and sigma squared, are the mean and the variance of our distribution respectively. Now, do any of you recognize this currency? This is a photo of the Deutschmark, the German currency until 2002, when it was replaced by the euro. And here we see a picture of Mr. Gauss, mathematician who, if you look carefully, came up with the equation for the normal or the Gaussian distribution. And it's so important that it was on the Deutschmark, the number 10 Deutschmark. He developed this formula in the early 19th century, although scientists had already noted for a long time that many natural phenomena had a symmetric distribution. And it looks, as we saw last time, like a bell. We had looked at the certain special properties that the normal distribution has. For example, it's asymptotic with respect to the x-axis. That means that as x gets very, very large or very, very small, the distribution approaches the x-axis but never crosses it. It is symmetric with respect to a vertical line, which occurs at the mean, x equals mu, and the maximum value of the function occurs exactly when the random variable x equals the mean. And also importantly, there's 2 points of inflection. And these are located at one standard deviation, one sigma distance on each side of the mean. So let's look again at simply what this distribution function means. So let's pretend you have a production factory which makes wooden tables. These wooden tables, these are used for big events, for example, like the Munich Oktoberfest. You need a lot of them. You control the quality of your production using a random variable x, and let's say that you're measuring the width of your tabletop in this production line. Your production is high quality. You have very top quality machines, but you know you can never have exactly the same tabletop width, because even with the best machines, there will always be a very slight variation of the tabletop widths. So our tabletop widths, if they are normally distributed, what does this mean? This means, so here we have our tabletop widths. Let that be our random variable x. This means our probability distribution function, we have a high probability, the highest probability, that most of our tabletop widths will be around the mean of the distribution, a mean value mu. Now, some will be larger and some will be smaller, but most will be centered around the mean. And as we get larger and smaller, we see that our probability will drop, going from a high value around the mean to a small value. What this means is that then we have a high probability that our tabletop widths will be near the mean and a low probability that our tabletop widths will be either very large or very short, very long or very short. We also have a symmetric distribution. We notice that we have the same probability to have a tabletop that is larger than the mean versus one that is smaller than the mean.